A single point of light can outshine a trillion stars. This is the raw power of a quasar, the universe's most energetic engine. Hidden at the heart of distant galaxies, these active galactic nuclei defy the very laws of physics as we know them. By the end of this journey, you will understand 25 of their most bizarre secrets, phenomena that stretch our comprehension of reality. How can something smaller than our solar system produce such impossible energy? And what happens when a star gets too close to the abyss? What cosmic mystery do you find most unsettling? Their brilliance is a cosmic affront to common sense. A single quasar, a tiny speck in the vastness, can radiate with the light of 1,000 Milky Ways, yet its engine room is smaller than the orbit of Pluto. This impossible brightness is our first great mystery. The secret does not lie in the black hole itself, for a black hole is the ultimate vault from which not even light can escape. The power is generated just outside the point of no return, in a maelstrom of matter known as an accretion disk. Picture a whirlpool of gas and dust, a cosmic hurricane spinning at nearly the speed of light. As material is dragged inward by the black hole's immense gravity, it piles up in this disk, superheating to millions of degrees through friction and colossal magnetic fields. This is not a gentle spiral, it is a violent, chaotic traffic jam where atoms are torn apart, releasing a torrent of radiation across the entire spectrum, from radio waves to lethal gamma rays. The efficiency of this process is staggering. While a star like our Sun converts less than 1% of its mass into energy through nuclear fusion, the accretion disk of a supermassive black hole can achieve an efficiency of up to 40%. This is the ultimate cosmic power plant, turning matter directly into light with a ferocity we can barely comprehend. It is this relentless conversion of entire stars and gas clouds into pure energy that allows a pinpoint of light to outshine every star in its home galaxy, casting a beacon across the universe that we can see from billions of light years away. But this cosmic engine has an even more violent outlet. From the very poles of this spinning vortex, the active galactic nucleus can fire out twin beams of pure energy, like the universe's ultimate blowtorches. These are relativistic jets, and they are among the most powerful structures we have ever observed. Composed of superheated plasma, these jets are not gentle streams. They are focused beams of particles accelerated to over 99% the speed of light, punching their way out of the galaxy and into intergalactic space. The scale is almost incomprehensible. A single jet can stretch for millions of light years, far beyond the boundaries of its own galaxy, sometimes plowing into other galaxy clusters with catastrophic force. So how does a black hole, an object famous for pulling everything in, manage to shoot matter out at such impossible speeds? The answer lies in the chaotic dynamics of the accretion disk and the immense magnetic fields it generates. As the disk of superheated gas spins at a furious rate, it twists the magnetic fields embedded within it, winding them up like cosmic rubber bands. These fields become so incredibly strong and tightly wound that they channel some of the infalling material away from the poles. It is a cosmic pressure release valve. Instead of falling into the black hole, this plasma is gripped by the magnetic fields and accelerated along a narrow, focused path, shooting out into the void. This process of collimation is what keeps the jet so incredibly straight and narrow over such vast distances, acting like a magnetic nozzle that prevents the energy from dissipating into a useless cloud. We see the effects when these jets slam into the thin gas that exists between galaxies. The impact creates colossal, glowing bubbles of radio emission that can be larger than the galaxies themselves. These jets are so energetic they can regulate star formation in an entire galactic cluster, heating the surrounding gas and preventing it from cooling and collapsing into new stars. It is a stunning display of feedback where a single object at the heart of a galaxy can dictate the fate of its entire neighborhood for eons. Yet for all their power, these jets can play a trick on our eyes, creating an illusion that shatters a fundamental law of physics. We observe blobs of plasma within these jets seemingly moving faster than the speed of light. This is superluminal motion, a cosmic mirage born from relativity. The reality is just as fascinating as the illusion. The jet is pointed almost directly at us, and the material within it is barreling toward us at a significant fraction of light speed. Imagine a runner on a moving walkway sprinting forward as the walkway itself moves. If that runner is coming almost straight at you, the combined motion makes them appear to cover the distance to you much faster than they actually could on their own. In the cosmic case, the light emitted from a later point in the blob's journey has a shorter distance to travel to reach us than the light from an earlier point, because the blob itself is chasing its own light. Our telescopes see the later emission arrive almost immediately after the earlier one, tricking us into calculating a speed that exceeds light's universal limit. It is a perfect storm of geometry and velocity, a relativistic sleight of hand that confirms Einstein's theories rather than breaking them. When this celestial alignment is perfect, and the jet of an active galactic nucleus is aimed like a searchlight directly at our solar system, we classify the object as a blazar. This is the most violent and variable class of active galaxy, a monster staring right at us, because we are looking straight down the barrel of the jet. Its emissions are massively amplified and incredibly intense. The light from a blazar is not steady. It can double in brightness in a matter of hours, flickering with a ferocity that betrays the unimaginable energies at work in its tiny central engine. This is not the gentle twinkling of a star, but the violent flare of a cosmic blowtorch. The variability is so extreme that it must be generated in a region not much larger than our own solar system, a breathtaking constraint on the size of such a powerful object. Blazars dominate the high-energy sky, pouring out not just visible light, but a torrent of gamma rays, the most energetic form of light in the universe. They are the most common sources of the mysterious high-energy gamma rays that our space telescopes detect, acting as distant, natural particle accelerators of almost unimaginable power. What other secrets might we uncover by staring directly into this cosmic beam? This flickering is not random noise. It is a direct window into the very heart of the maelstrom. The rapid and unpredictable brightness changes we observe in quasars, sometimes occurring over mere days or weeks, impose a strict limit on the size of their central engines. Light can only travel so far in a given time, a concept known as light travel time. If a quasar doubles its brightness in 48 hours, the region responsible for that flare cannot be much larger than the distance light travels in 48 hours, which is about the size of our solar system. This forces the energy of 1 trillion stars to be generated in a space so compact it defies all intuition. The flicker is the signature of a feeding frenzy, the chaotic clumping and final death spiral of matter in the turbulent accretion disk. But sometimes the changes are far more dramatic, leading to an even deeper mystery. Astronomers have discovered what they call changing-look quasars. These are not mere flickers. Over months or years, a brilliant quasar can seem to vanish, its characteristic broad emission lines disappearing from its spectrum, only to roar back to life later. It is as if the cosmic engine has a dimmer switch, one that can be turned down so low the quasar appears to be just a normal, quiet galaxy. The leading theory suggests this happens when the black hole's food supply is suddenly cut off. A large, final clump of matter might fall in, creating a brilliant last feast, after which the accretion disk simply runs out of fuel. Without a continuous supply of superheated gas, the brilliant beacon fades, and the active galactic nucleus goes silent. Then, millions of years later, another star or gas cloud might wander too close, restarting the entire violent cycle. This on-again, off-again behavior reveals that the active phase of a galactic nucleus is not a permanent state, but a temporary, if spectacular, chapter in a galaxy's long life. The most violent and direct way to start such a chapter is through a stellar cataclysm known as a tidal disruption event. Picture a star, much like our own Sun, on a stable orbit for billions of years. Its path takes it just a little too close to the supermassive black hole lurking in the galactic center. As it approaches, the side of the star facing the black hole feels a much stronger gravitational pull than the side facing away. This difference in force, the tidal force, stretches the star horizontally while compressing it vertically. The star is not just pulled apart, it is spaghettified, stretched into a long, thin stream of hot gas. About half of this stellar debris is flung out into space, while the other half falls back onto the black hole, forming a temporary, incredibly bright accretion disk and a brilliant flare of light that can outshine its entire host galaxy for many months. This is the birth of a temporary active galactic nucleus, a brilliant flash marking the death of a star and the brief awakening of a sleeping giant. We are witnessing in real time the process that may ignite and feed these cosmic monsters. These brilliant flares and flickers are signals from across the cosmos, but their journey to our telescopes is anything but direct. The light from a distant quasar carries an imprint of every structure it has passed through, a ghostly record written in its very colors. When astronomers split this light into a rainbow-like spectrum, they find it is not a clean, continuous band. Instead, it is scarred by thousands of dark absorption lines, a phenomenon so dense it is called the Lyman-Alpha Forest. Each one of these lines is a cosmic shadow, cast by a single cloud of neutral hydrogen gas that floated between the quasar and us. As the quasar's light travels for billions of years through the vast emptiness between galaxies, it passes through this diffuse, filamentary web of primordial gas. When the light hits a specific energy that hydrogen can absorb, a tiny portion is stolen, leaving a telltale dip in the spectrum at a very specific wavelength. Because the universe is expanding, light from more distant clouds is stretched more, shifting each absorption line to a different position. The result is a dense thicket of lines, each one representing a different cloud at a different distance. It is a core sample of the cosmos, a single beam of light that has recorded a map of the universe's large-scale structure across billions of light years. This forest is not a random collection of clouds. The patterns in the lines reveal that the hydrogen is arranged in vast sheets and filaments, the cosmic web that forms the backbone of the universe. The empty regions, the great cosmic voids, appear as clearings in this spectral forest where the absorption lines thin out. By reading this forest, astronomers can study the properties of the intergalactic medium itself, the tenuous gas that is the raw material for all future galaxies and stars. It tells us about the temperature, density, and composition of the space between everything, a realm that would otherwise be completely invisible. This phantom structure, painted in shadows on the brilliant light of a quasar, is one of our most powerful tools for understanding the architecture of the cosmos on the very largest scales. Those ghostly absorption lines are more than just a map, they are a clock. The light from the most distant quasars carries a signature of cosmic expansion written directly into its color, a phenomenon known as redshift. As the universe stretches, it stretches the very light traveling through it, shifting its wavelength toward the red end of the spectrum. The farther the light has traveled, the more stretched it becomes. Quasars, with their incredible brightness, became the perfect beacons to observe this effect across vast distances. Their high redshifts were one of the key pieces of evidence that we live in an expanding universe, one that is continuously growing larger. But this discovery was not without its fierce controversies. When quasars were first identified, their enormous redshifts suggested they were incredibly far away and therefore unbelievably powerful. Some scientists refused to accept that such tiny objects could outshine entire galaxies, proposing instead that the redshift was caused by some unknown local effect or that quasars were much closer than their light implied. It was a cosmic debate that raged for years, a battle between established intuition and staggering new evidence. The the resolution came from painstaking observation. Astronomers found quasars that were clearly linked to distant galaxies sharing the same immense redshift, proving their true cosmological distances. This confirmed that their brilliance was real, forcing us to accept the existence of these monstrous engines. Once their distance was settled, a new possibility emerged. Could we use these brilliant beacons as cosmic mileposts? The quest to use them as standard candles, however, proved tricky. A perfect standard candle is an object with a known, consistent intrinsic brightness. By comparing how dim it appears to us with how bright we know it truly is, we can calculate its distance, but quasars are notoriously unruly, their luminosities varying wildly from one to another. One quasar might be 1,000 times brighter than another at the same redshift, depending on how much its black hole is feeding. So how can such a chaotic object be used for precise measurement? The key was not in the quasars themselves, but in the shadows they cast. Remember the Lyman-Alpha Forest, that dense collection of absorption lines. The specific pattern of this forest, the distribution of its lines, is directly related to the density of matter in the universe at the time the light passed through it. By analyzing these patterns in great detail, astronomers can essentially use the quasar's light as a probe to measure fundamental cosmic parameters, including the rate of the universe's expansion. In this way, quasars have transitioned from being controversial oddities to essential tools in our quest to understand the cosmos, their light serving as both a message from the early universe and a ruler to measure its growth. What other cosmic truths are hidden within their brilliant, chaotic glow? This brilliant glow from the early universe presents us with a profound timing problem. When we look at the most distant quasars, we are seeing them as they were when the cosmos was less than 1 billion years old, a mere infant by cosmic standards. Yet these objects are already monstrous, harboring supermassive black holes with masses billions of times that of our Sun. How could something so colossal form so quickly? This is the black hole mass paradox, a cosmic race against time that challenges everything we think we know about how these giants are born and grow. According to standard models, a black hole starts from the collapse of a single massive star, forming a stellar mass black hole of perhaps a few dozen solar masses. To grow into a billion solar mass behemoth, it would need to feast continuously on gas and stars, gobbling up matter at its maximum possible rate for nearly the entire age of the universe. But the oldest quasars prove this is impossible because they achieved their immense size when the universe was far too young for this slow and steady process. It is like finding a fully grown ancient redwood tree in a forest that is only a few years old. The math simply does not add up, so what is the solution? Did these black holes have a head start? One compelling idea is that the seeds for these monsters were not ordinary stellar remnants, but something far more exotic and primordial. In the chaotic first moments after the Big Bang, immense pockets of dense gas could have collapsed directly, skipping the star formation phase entirely and birthing black holes with masses of tens of thousands of suns right from the beginning. These direct collapse black holes would have been born hungry, giving them a massive initial advantage in the race to grow. Another possibility is that the early universe was a far more violent and crowded place than we imagined, with frequent mergers between these early seed black holes and dense, gas-rich galaxies. In this environment, growth could have been explosive, a runaway feeding frenzy where the black hole gorged itself on a near-limitless supply of cold, dense gas. Perhaps the laws of physics themselves allowed for a different mode of feeding, where the black hole could consume matter at a supercritical rate, breaking the usual limits without blowing away the surrounding gas with its own radiation. The existence of these ancient giants forces us to reconsider the very first chapters of cosmic history, suggesting a dawn of the universe that was far more dramatic and efficient at building monsters than we ever dreamed. This immense power does not just light up the cosmos, it actively sculpts it. the energy pouring from a quasar can travel back to its own host galaxy, a process known as quasar feedback. It is a cosmic dialogue between the monster and its home, a conversation that can either nurture life or sterilize an entire galaxy. The outcome depends entirely on the intensity of the outburst. In one scenario, the quasar's relativistic jets and intense radiation can compress cold, dense clouds of gas throughout the galaxy. This compression acts as a trigger, a cosmic push that initiates the collapse of these clouds and sparks a firestorm of new star formation. In this mode, the quasar is a creative force, a galactic midwife helping to birth entire generations of stars. But there is a far more destructive side to this relationship. When the quasar enters an extremely violent feeding phase, the energy output becomes catastrophic. The radiation pressure from the accretion disk is so intense that it physically pushes against the surrounding gas, driving powerful winds that can blow at thousands of kilometers per second. These are not gentle breezes, they are hurricane-force outflows that can sweep an entire galaxy clean of its star-forming fuel. Imagine a cosmic gardener who not only uproots the weeds but also blows away all the topsoil, ensuring nothing can grow again for eons. This is quenching. The galaxy, robbed of the cold gas needed to form new stars, slowly reddens and dies. Its stellar population ages without renewal, transforming a vibrant, blue, star-forming spiral into a passive, red and dead elliptical galaxy. This feedback loop solves a great mystery in astronomy. For years, cosmologists wondered why the largest galaxies in the universe seemed to have shut down their star formation so early in cosmic history. The answer appears to be these brilliant, terrifying beacons at their centers. The quasar, in its most violent act of self-expression, can seal the fate of its own galaxy, demonstrating that the most powerful engine in nature holds the power of life and death over its cosmic neighborhood. That galactic sculptor can also become a cosmic lens, warping the very fabric of space around it. The immense gravity of a quasar and its host galaxy does not just pull on matter, it bends the path of light itself. This effect, predicted by Einstein, transforms the quasar into a natural telescope, revealing objects that would otherwise be far too faint and distant for us to see. When a distant quasar sits almost perfectly in line with an even more distant galaxy, the foreground quasar's gravity curves the space around it. The light from the background galaxy, traveling in what it thinks is a straight line, follows this curved path on its journey to us. We do not see a single, clear image of that faraway galaxy. Instead, we see multiple, distorted and magnified copies of it, arranged in a perfect circle or a cross of light known as an Einstein ring. It is a celestial mirage, a trick of gravity that breaks a single source into a cosmic collage. These multiple images are not just a beautiful curiosity. They are a powerful tool for astronomers because the light for each image takes a slightly different path around the gravitational lens. The images flicker at slightly different times. By carefully monitoring these time delays, scientists can perform a remarkable calculation. They can measure the precise distance to the lensing quasar itself, providing an independent check on our cosmic distance ladder and the expansion rate of the universe. Furthermore, the exact shape of the distorted images holds a secret. The degree of warping depends on the total mass of the lensing system, the quasar's galaxy. But when astronomers add up all the visible matter, stars and gas, they find it is not nearly enough to create the observed bending. The rest of the gravity, the majority of it, must come from something invisible. This is one of the strongest pieces of evidence for the existence of dark matter, the mysterious substance that makes up most of the mass in the universe. By studying these gravitational arcs and rings around quasars, we are not just seeing a distant light show, we are mapping the distribution of the unseen scaffolding that holds the cosmos together. This cosmic menagerie of quasars, blazars, and radio galaxies presents a bewildering diversity. Yet, what if this entire zoo of active nuclei is an illusion of perspective, a single kind of cosmic engine that merely looks different depending on our angle of view? This is the elegant idea behind the unified model of active galactic nuclei. At its heart is a supermassive black hole and its brilliant accretion disk, the universal power source. Surrounding this inner engine is a thick, donut-shaped ring of gas and dust called the torus. This structure is not a gentle cloud, but a dense, obscuring shroud that dictates everything we see from Earth. Imagine a brilliant lighthouse in the middle of a dense, circular fog bank. If you are positioned high above the fog, looking straight down onto the lighthouse, you see its unfiltered, blinding beam. In the cosmic analogy, this is a blazar where we stare directly down the powerful relativistic jet. If your view is from the side but still above the fog bank, you can see the bright lighthouse itself clearly. This is a quasar or a Seyfert galaxy, where we have a direct, unobscured view of the intensely hot accretion disk. Now, imagine your line of sight is through the thickest part of the fog bank itself. The brilliant central light is completely blocked, hidden from view. All you can see are the effects of the lighthouse's beam as it illuminates the top and bottom of the fog from within, or perhaps the glow from the surrounding harbor. This is a radio galaxy where our view to the central engine is blocked by the torus, and we only observe the giant lobes created by its jets. The unified model elegantly explains why some active galaxies show broad, turbulent emission lines in their spectra from fast-moving gas near the black hole, while others show only narrow, calm lines from slower, more distant gas. In the first case, we see the inner region directly. In the second, the torus physically blocks our view of that inner chaos, and we only see the slower gas from the outer regions. The angle from which we observe a single, universal structure determines its entire classification, turning a chaotic collection of objects into a simple, beautiful family portrait. What other cosmic complexities might be resolved by a simple shift in our point of view? That phantom forest of absorption lines is more than a cosmic core sample. It is a treasure map pointing to a hidden fortune. For decades, astronomers faced a baffling accounting problem. When they tallied up all the ordinary matter in the universe, the atoms that make up stars, planets, and our own bodies, a huge portion was simply missing. The census of visible objects fell dramatically short of the total amount of matter we know must exist from other measurements. This was the case of the missing baryons. The solution to this cosmic mystery was found hiding in plain sight, written into the quasar's light. The countless absorption lines of the Lyman-Alpha Forest were the key. They revealed that a vast amount of ordinary matter was not in bright galaxies, but spread throughout the voids between them in a diffuse, incredibly hot web of gas. This is the warm-hot intergalactic medium, or WIM. Imagine a steamy, muggy day where the air is thick with invisible water vapor. The WIM is the cosmic equivalent, a fog of superheated gas that fills the spaces of the cosmic web. Its temperature is staggering, reaching millions of degrees, which makes it incredibly difficult to observe directly. At such high temperatures, the gas does not glow brightly in any single wavelength. It just emits a faint, diffuse X-ray glow that is nearly impossible to distinguish from the background. But when the brilliant, pure light of a distant quasar passes through this hot fog, the gas leaves its fingerprints. Specific elements within the WIM, like highly ionized oxygen and neon, absorb very particular energies of the quasar's ultraviolet and X-ray light. Each element steals a tiny, specific piece of the quasar's brilliance, creating a new set of faint absorption lines in the spectrum. By hunting for these subtle, telltale dips, astronomers can confirm the presence, temperature, and density of this elusive material. It is like using a brilliant spotlight to illuminate a faint, wispy fog that would otherwise be completely invisible. Through this method, we have finally located the universe's missing atomic matter. It was never truly gone. It was just hiding in the hottest, most tenuous corners of space, revealed only when backlit by the most powerful beacons in the cosmos. The winds that blow from a quasar are not like any breeze we know. They are ultra-fast outflows, hurricanes of ionized gas screaming away from the galactic center at velocities that defy belief. Some of these cosmic gales reach speeds of 20 or even 30% of the speed of light, carrying with them the energy to reshape entire galaxies. This is not a gentle push, it is a firestorm. These winds originate frighteningly close to the supermassive black hole, likely launched from the inner regions of the accretion disk itself by the combined fury of intense radiation pressure and magnetic forces. As matter spirals inward, the sheer brightness of the disk creates an outward push so powerful that it overcomes the black hole's immense gravity, hurling material back out into space. The energy involved is staggering. A single outflow can carry away more energy in 1 second than our Sun will produce in its entire 10 billion-year lifetime. This constant, violent expulsion does more than just dim the quasar's brilliance by robbing the black hole of its fuel. It slams into the surrounding reservoirs of cold gas, the very raw material for new stars. The impact is catastrophic, heating the gas to such extreme temperatures that it can no longer collapse to form stars. This is quasar feedback in its most direct and destructive form, a self-regulating mechanism where the black hole's own growth frenzy ultimately shuts down the very process that feeds it. But the story does not end within the galaxy. These ultra-fast outflows blast their enriched contents far beyond the galactic borders, carrying heavy elements like carbon, oxygen, and iron forged in the hearts of stars and supernova. They travel for millions of light years, seeding the barren intergalactic medium with the building blocks of planets and life. The iron in your blood, the oxygen in your lungs, some of those atoms were once part of a star that was torn apart, swallowed by a black hole, and then violently expelled in a quasar's wind, sent on a billion-year journey to eventually become part of you. The violence of a single quasar is staggering, but sometimes the universe doubles down on chaos. Astronomers have spotted pairs of these brilliant beacons shining in incredibly close proximity, cosmic twins separated by a distance smaller than the span of their own host galaxies. These quasar pairs are a rare and spectacular sight, and they hint at a titanic gravitational dance unfolding at their core. The leading explanation is that we are witnessing a binary system of two supermassive black holes, each with its own raging accretion disk orbiting one another. This bizarre configuration is the direct result of a galactic collision. When two large galaxies merge, their central black holes are dragged together by gravity and interstellar friction, eventually sinking to the new common center. For a time, both black holes can be actively feeding on the vast reserves of gas stirred up by the galactic crash, lighting up as a pair of quasars. Observing such a system is like catching a glimpse of the final act in a cosmic ballet that has lasted for billions of years. The separation between these quasar pairs tells a story of slow, inevitable decay. As the black holes whirl around each other, they lose energy by slinging stars away through complex gravitational interactions. This slow drain of energy tightens their orbit, bringing them ever closer. Eventually, they enter a phase where their fate is sealed by the emission of gravitational waves, ripples in the very fabric of spacetime predicted by Einstein. The final merger of two supermassive black holes would be the most powerful gravitational wave event in the universe since the Big Bang, a storm of space-time vibrations that future observatories hope to detect. Yet, finding these pairs is notoriously difficult. The separation on the sky is so minute that it often requires the sharpest eyes of the Hubble Space Telescope or sophisticated statistical techniques to distinguish two distinct points of light from one. Confirming a true binary is an even greater challenge, as a single quasar's light can be split by an intervening galaxy acting as a gravitational lens, creating a convincing but false pair. When a genuine binary is confirmed, it offers a priceless laboratory. The orbital dynamics of these monsters can reveal the properties of the dark matter halo that anchors them, and their feeding habits show us how galaxy collisions funnel vast amounts of material into the hearts of darkness. What cosmic symphony would we hear if we could listen to the final moments before these two giants become one? That cosmic symphony of colliding giants is framed against the most ancient light in the universe, a background canvas that holds its own strange signature. This is the cosmic microwave background radiation, the faint afterglow of the Big Bang. It appears nearly identical in every direction we look, a testament to the universe's uniformity, but it holds a subtle, vital imperfection known as the dipole anisotropy. Imagine you're walking through a gentle, steady rain. If you stand still, the raindrops hit you evenly from all directions, but if you start running forward, you will feel more drops hitting your front than your back. The rain appears to be coming from a preferred direction because of your own motion. This is precisely what happens with the cosmic microwave background. Our entire solar system is not sitting still. We are moving at a staggering 600,000 kilometers per hour relative to this primordial light. This motion creates a Doppler effect. In the direction we are heading, the microwave background photons are blue-shifted, squeezed to a slightly higher temperature. In the opposite direction, the direction we are fleeing, the photons are redshifted, stretched to a slightly cooler temperature. This temperature difference is tiny, only about 0.003 of a degree, but it is unmistakable. It creates a hot pole and a cold pole in the sky, the cosmic dipole. But here is where quasars enter the story with profound implications. For decades, the standard reference frame for measuring this motion, our velocity through the cosmos, was based on the cosmic microwave background itself. It was the ultimate anchor. However, a new and more precise celestial reference frame has been established using the precise positions of distant quasars observed by radio telescopes. Quasars are so immensely far away that their collective motion is negligible, making them the perfect fixed points to define a truly stationary grid for the universe. When astronomers used this new quasar-based frame to check our motion, they found a puzzling and persistent tension. The velocity measured from the cosmic microwave background dipole does not perfectly align with the velocity measured against the quasar frame. The direction is close, but the speed seems to be a bit off. This discrepancy is a small but nagging mystery in modern cosmology. It could be a sign of subtle systematic errors in our measurements, or it could be something far more exciting. Perhaps it hints that the dipole is not entirely due to our motion. A small part of it might be intrinsic, a genuine fluctuation imprinted on the universe from its earliest moments, a relic from a time before the first stars or galaxies even existed. This tiny imperfection in the oldest light we can see, measured against the fixed grid of the most distant quasars, reminds us that even our most fundamental cosmic maps are still being refined, and that the universe always has one more secret to share. This ability to illuminate the cosmic void makes quasars the ultimate celestial backlights. Their brilliant, distant glow acts like a scientific spotlight, allowing us to study every wisp of gas and every cosmic structure that falls in the line of sight between them and our telescopes. We are not just observing the quasars themselves, we are reading the shadows they cast, turning their light into a diagnostic tool for the entire universe. One of the most intimate things we can study is the gas within the quasar's own host galaxy. While the brilliant nucleus outshines everything, its light, as it streams outwards, passes through the galaxy's own halo of gas. Atoms in this halo absorb specific wavelengths, imprinting a unique signature onto the quasar's spectrum. By analyzing these absorption lines, astronomers can determine the composition, temperature, and motion of the galactic gas. They can see vast winds blowing outwards from the galaxy, measure the abundance of heavy elements forged in stellar furnaces, and even spot giant clouds of cold gas that are the raw material for future stars. It is like analyzing a distant city's atmosphere by studying how its bright central stadium lights filter through the urban smog. But the reach of this technique extends far beyond a single galaxy. The same principle allows us to probe the truly large-scale structure of the universe, the cosmic web of filaments and voids that defines the distribution of matter. When we look at the spectrum of a single distant quasar, we see that forest of absorption lines, each one a cloud of hydrogen in the intergalactic medium. Now imagine pointing telescopes at two different quasars that are very close together in the sky. The light from each one will pass through a slightly different path through the cosmic web. By comparing the two absorption forests, scientists can map the three-dimensional structure of this vast, invisible network. They can measure how the gas is clustered along the filaments and how empty the voids truly are, creating a tomographic map of the universe on the grandest possible scale. This technique has even allowed us to witness one of the universe's great phase transitions, the final act of cosmic reionization. After the Big Bang, the universe cooled and settled into a dark age filled with neutral hydrogen gas. Then the first stars and galaxies ignited, and their intense ultraviolet radiation began to tear apart those neutral atoms, reionizing the cosmos and making it transparent to light. The final chapter of this process involved the ionization of helium, which requires even more energetic radiation. The signature of this helium reionization is etched into the light of the most distant quasars. At a certain redshift corresponding to a time when the universe was roughly 3 billion years old, astronomers see a specific absorption signal from singly ionized helium suddenly disappear. This tells us that the space between galaxies became flooded with such intense high-energy radiation that it stripped the second electron from every helium atom. The prime suspects for providing this brutal energy are the quasars themselves. Their extreme ultraviolet radiation is one of the few forces powerful enough to complete this cosmic task, meaning these brilliant beacons did not just light up the early universe, they fundamentally changed its chemical state, carving out the transparent cosmos we observe today. Sometimes the universe's most powerful engines sound a very specific note. Within the chaotic radio chorus of active galactic nuclei, a few peculiar sources stand out because their radio emission is not a smooth roar, but a sound that peaks and then fades at a very specific frequency, around a few gigahertz. This is the gigahertz peaked spectrum, a phenomenon that acts like a cosmic fingerprint for a very specific type of object. The reason for this strange peak is self-absorption. Imagine a dense, compact fog bank so thick that the light and radio waves generated inside it cannot easily escape. The fog absorbs its own emission. At lower frequencies, the radio waves are trapped, unable to break free from the dense plasma that creates them. At higher frequencies, the waves can finally pierce through, but the intrinsic emission from the source itself is weaker. The peak occurs at the precise frequency where the fog becomes just transparent enough for the maximum amount of radio energy to escape. This tells us that the source is incredibly small and incredibly dense, a young, overpressured bubble of plasma still confined within the heart of its host galaxy. It is a sign of a central engine that has recently turned on, its first outburst still bottled up by their own intense nature. This youth is even more apparent in a related class of objects known as compact symmetric objects. These are some of the most enigmatic sources in the radio sky. They appear small, often less than a few thousand light-years across, which in cosmic terms is remarkably compact. When we map them with very long baseline interferometry, creating a radio picture with incredible resolution, they show a beautiful and baffling symmetry. We see two bright lobes of radio emission, one on either side of a central core, and often jets pointing directly from the core to each lobe. The symmetry is the key clue. In older, larger radio galaxies, the jets and lobes are almost never perfectly symmetrical. One side appears brighter and closer because its jet is pointed toward us, benefiting from relativistic effects, while the other, receding jet appears fainter. But in a compact symmetric object, both sides are nearly identical in brightness and distance from the center. This suggests we are seeing the system almost perfectly from the side, and more importantly, we are seeing it at a very early stage in its life. The twin lobes are the advancing shock fronts from a recent outburst, plowing into the surrounding interstellar medium. They are so young, perhaps only a few thousand years old, that they have not had time to be distorted by motion or by interacting with an uneven galactic environment. These objects may represent the infancy of a giant radio galaxy, caught in the first moments after its central black hole has launched its first major jets. We are witnessing the birth cries of a cosmic powerhouse, a fleeting stage in a life cycle that will last for millions of years. What would it be like to watch such a young engine mature and reshape its galactic home over eons to come? For all their cosmic drama, quasars often hide within surprisingly ordinary homes. The brilliant beacon at the galaxy's heart can be so intense that it completely drowns out the collective light of its host, making the surrounding galaxy nearly invisible to our telescopes for decades. Peering past that glare to see the quasar's true neighborhood was one of astronomy's great technical challenges. The breakthrough came with the sharp vision of the Hubble Space Telescope, which finally managed to block the central point of light and reveal the faint, sprawling structures surrounding it. The results were a surprise. These are not all chaotic, war-torn galaxies. Many quasars reside in perfectly normal-looking elliptical galaxies, vast cities of old, red stars that have finished their star-forming lives. Others are found in beautiful spiral galaxies, much like our own Milky Way, with graceful arms laced with blue, newborn stars and glowing pink clouds of hydrogen gas. This diversity tells us that the conditions for igniting a quasar are not exclusive to one particular galaxy type. The common thread is not the galaxy's shape, but the presence of fuel and a trigger. A supermassive black hole can lie dormant for eons, a sleeping giant in a quiet galaxy. What awakens it is a sudden, massive infusion of gas. This is why we so often find quasars in galaxies that are interacting or merging. Picture two great spiral galaxies, each with its own central black hole, beginning a slow, gravitational dance that lasts for hundreds of millions of years. As they swing past each other, their delicate structures are torn apart by tidal forces. Vast streams of gas and dust are pulled from their orbits and funneled directly toward the galactic centers. This cosmic rainfall provides a feast for the dormant black holes, igniting their accretion disks and lighting up the brilliant quasar. The merger provides the chaos and the fuel delivery system required to awaken the monster. This explains why the peak of quasar activity in the universe's history coincided with an era of frequent galactic collisions, when the cosmos was younger, denser, and more violent. A quasar, then, is less about the type of galaxy and more about a specific, dramatic event in a galaxy's life. It is the signature of a galaxy experiencing a profound transformation, often a final, brilliant burst of activity before its star-forming fuel is either consumed or blown away, leaving it to settle into a quiet, mature state. The most powerful engines in the universe are not born in special factories, but can flare to life in almost any neighborhood given the right cosmic push. This dazzling variety of quasars is not a random collection. Hidden within their seemingly chaotic properties is a subtle order, a cosmic classification system written in their own light. Astronomers call this the quasar main sequence, a pattern that connects how fast a black hole is feeding to the shape and strength of its surrounding gas clouds. It is a fundamental relationship that helps us make sense of the entire active galactic zoo. At its heart are two key properties. The first is the accretion rate, which is essentially how voraciously the black hole is consuming matter. The second is the orientation of our line of sight, which determines how much of the inner chaos we can actually see. But there is a third crucial factor, the physical structure of the broadline region, the cloud of fast-moving gas that orbits perilously close to the black hole itself. This region is not a uniform sphere. It is thought to be a thick, puffy disk or even a collection of dense, discrete clouds. The shape and density of this structure change systematically with the black hole's feeding style. When a black hole is feasting at a high rate close to its theoretical maximum, the intense radiation pressure from the brilliant accretion disk actually puffs up the broad line region, making it more spherical and dense. This produces very broad, strong emission lines in the quasar's spectrum. In this state, the quasar's appearance is dominated by the sheer power of its accretion. If our view is face-on, looking directly into this energetic core, we see a classic bright quasar. If the black hole is eating at a much more modest pace, the radiation pressure is weaker. The broad line region does not get puffed up. Instead, it collapses into a thinner, flatter disk. The emission lines we see from this flatter structure are narrower and weaker. In this low accretion state, the quasar's appearance becomes much more sensitive to our viewing angle. If we look from the side through the thin part of the gas disk, we see those narrow lines. But if we look from above or below, our view is relatively unobstructed, and we still see a bright continuum of light from the accretion disk itself. This elegant sequence ties together objects that once seemed completely unrelated. It explains why some quasars have incredibly broad emission lines while others have narrow ones, and why this correlates with other properties like the shape of their spectral energy distribution. It is a unifying framework that shows how a single underlying engine, a supermassive black hole with an accretion disk and a structured gas cloud, can produce the entire spectrum of active galaxies we observe simply by changing its feeding habits and the angle from which we watch it. This cosmic menu, from a gluttonous feast to a modest snack, dictates the entire character of the universe's most brilliant beacons. That flickering pattern, the very signature of a quasar's chaotic heart, holds a secret clock. Its rhythmic pulses, or lack thereof, provide a direct measurement of time itself stretching across the cosmos. We see quasars at immense distances flicker with a certain characteristic speed, a tempo set by the physics of their inner accretion disks. But when we look back to quasars in the early universe, their flickering appears to slow down. It is not that the engines themselves are running slower, but that the very fabric of spacetime has expanded during the billions of years it took their light to reach us. This is cosmological time dilation in action, a profound prediction of Einstein's general relativity. The expansion of the universe does not just stretch the wavelength of light, making it redder, it also stretches the time between events. A flash of light that took 1 day to occur in the quasar's rest frame might appear to take 10 days from our perspective here on Earth, because the space through which the light's information is traveling has itself been stretched. This effect has been confirmed by studying the light curves of distant supernovae, but detecting it in quasars was a greater challenge because their variability is so chaotic. How do you measure the slowing of a clock that has no regular tick? Astronomers solved this by analyzing the statistical properties of the flickering. They looked at the overall structure of the light curves, measuring how quickly the brightness tends to change over time. When they compared quasars at different redshifts, a clear pattern emerged. The light curves of the most distant, ancient quasars were statistically more stretched out, their changes happening over a longer observed time frame than in nearby quasars. This is the universe putting its thumb on the scale of time, slowing down the perceived rhythm of these cosmic engines the farther back we look. It is a direct confirmation that we live in an expanding universe, one where time itself is not a constant river but a stream that flows at different rates depending on the cosmic landscape. The quasar's clock ticks slower not because of any local effect, but because the entire cosmos has grown since that tick began its journey to us. This observation ties the large-scale fate of the universe directly to the behavior of its most energetic objects, a fundamental link between the very large and the incredibly small. The silent, invisible architecture of the cosmos may hold the ultimate key to these brilliant engines. every galaxy, including our own Milky Way, is cocooned within a vast spherical halo of dark matter, a ghostly gravitational scaffold that dictates its very existence. The properties of this halo, its mass and its concentration, seem to be intimately linked to the growth of the supermassive black hole at its center. It is a cosmic partnership forged by gravity, where the unseen controls the destiny of the unseen. A more massive dark matter halo creates a deeper gravitational well, pulling in more ordinary gas from the surrounding cosmic web over billions of years. This provides a larger reservoir of fuel for the central black hole to eventually consume. But the halo's influence is more nuanced than just providing a larger pantry. The way a halo grows through a series of mergers with smaller halos directly fuels the black hole's activity. Each merger shakes up the settled gas within the galaxy, driving torrents of it inward toward the waiting giant. This is why we so often see quasars flaring to life during galactic collisions, the dark matter halo orchestrating the chaotic dance that delivers the feast. The relationship goes even deeper. Observations reveal a tight correlation between the mass of the central black hole and the properties of the galaxy's central bulge of stars. Since the bulge itself forms within the dark matter halo's grip, this implies a fundamental connection between the invisible halo and the black hole it anchors. The dark matter sets the rules of the game, establishing the gravitational environment that governs how efficiently gas can flow all the way to the very center to feed the monster. This cosmic feedback loop suggests that dark matter does not just build the galaxy's skeleton, it also midwives the birth and regulates the growth of its most powerful engine. Could the specific density profile of a dark matter halo determine whether a black hole becomes a quiet giant or a brilliant quasar? The answer may lie in the earliest moments of the universe, where the first dark matter structures formed the seeds around which everything else, including these cosmic behemoths, would eventually coalesce. This brilliant age of quasars could not last forever. Across the cosmos, their numbers began to plummet after a specific point in time, corresponding to a redshift of about 2. The universe's most dazzling era of fireworks was drawing to a close. The primary reason for this great dimming is a simple cosmic reality: the fuel was running out. In the early, dense universe, galaxies were gas-rich and frequently colliding, providing a near-endless buffet for supermassive black holes. But as the cosmos expanded, these prime feeding grounds became scarcer. Galaxies settled into more stable, isolated orbits, and the vast reservoirs of cold, dense gas necessary to power a brilliant quasar were either consumed in earlier feasts or heated to such extremes that they could no longer easily fall inward. It was a cosmic energy crisis where the most powerful engines simply ran out of the raw material they needed to shine. But the black holes were not just passive victims of this famine, they were active participants in their own starvation. The intense quasar feedback we discussed earlier played a crucial role in this decline. Each brilliant outburst drove powerful winds that swept the host galaxy clean of star-forming fuel, effectively slamming the pantry door shut. After a period of intense activity, a black hole could literally blow away its own food supply, forcing itself into a state of hibernation. This created a self-regulating cycle where periods of brilliant activity were inevitably followed by long eons of quiescence. The universe transitioned from a wild youth dominated by brilliant, feeding monsters to a more sedate adulthood where supermassive black holes, for the most part, slumber quietly. The active galactic nuclei we see in the modern universe are often just faint echoes of that glorious past, their engines sputtering on a much leaner diet. The Great Quasar era ended not with a bang, but with a gradual fading as the cosmic conditions that gave rise to these magnificent beasts fundamentally and permanently changed. Their brilliant era may be over, but the legacy of quasars is written into the very future of the cosmos. the energy they released over billions of years did more than just light up the early universe, it fundamentally cooked the cosmic pot. By pouring radiation and hot gas into the vast intergalactic voids, quasars helped raise the universe's temperature, making it increasingly difficult for new gas to cool, collapse, and form stars in the most massive galaxies. This relentless heating is one reason the golden age of star formation is also behind us. The universe is gradually transitioning from a vibrant, blue place filled with young stellar nurseries to a redder, more sedate state dominated by older, dying stars. In this grand narrative, quasars acted as a cosmic regulator, their outbursts helping to quench star formation in the largest galaxies and effectively setting a limit on how big a galaxy can ultimately become. But what of the supermassive black holes themselves, the dormant engines at the center of this story? In our local, modern universe, they are mostly quiet, like sleeping dragons. Yet given enough time, measured in trillions of years, even these giants will meet their end. Through a theoretical process known as Hawking radiation, a black hole slowly loses mass, evaporating over unimaginable timescales. A black hole with the mass of a few suns would take longer than the current age of the universe to evaporate, but one with billions of solar masses would require a span of time so vast it defies human comprehension. In this almost infinitely distant future, the final act of a supermassive black hole might be a silent pop, a flash of particles in an otherwise dark and empty cosmos. Long before that, in the expanding universe forecast by our current models, galaxies beyond our local group will accelerate away, their light red shifting into invisibility. The night sky for any future civilization in the Milky Way will grow steadily darker, the last quasars and distant galaxies fading from view entirely. The brilliant, active chapters of the universe, the epochs of quasar light and galactic collisions, will become a frozen memory in an ever-cooling, ever-quieter cosmos. The echoes of these mighty engines will have shaped everything that came after, leaving behind a universe whose structure and very fate were forged in their incredible, violent light. The quest to understand these cosmic monsters is far from over. Our next generation of observatories, with vision sharper than ever before, are poised to stare even deeper into the dawn of time. The James Webb Space Telescope, with its infrared eyes, is already piercing the cosmic dust that shrouded the first galaxies. It seeks the very first quasars, those that ignited when the universe was a mere infant of a few 100 million years old. By capturing their faint, red-shifted light, Webb can dissect the composition of the gas swirling into these primordial black holes. It will reveal what the early universe was made of and how the first heavy elements were forged and spread by their tremendous winds. We will see not just the brilliant beacon, but the infant galaxy struggling to form around it, giving us a complete picture of how these monsters and their homes grew up together. Meanwhile, on the ground, the square-kilometer array will open its ears to the radio sky on an unprecedented scale. This vast network of antennas will map the universe not in light, but in the long, slow waves of radio emission. It will trace the hydrogen gas that filled the early cosmos, spotting the voids and filaments of the cosmic web with breathtaking precision. When a distant quasar's light passes through this web, the square-kilometer array will see the subtle shadows in exquisite detail, allowing us to watch the process of reionization as it happened, a cosmic dawn filmed in real time. It may even detect the faint, whisper-like signal from neutral hydrogen around the very first quasars, showing us the pristine gas that first collapsed to feed them. Together, these giants of astronomy will tackle the great remaining puzzles. They could finally find the direct collapse black hole seeds, the missing link in the story of how supermassive black holes grew so big so fast. They will watch quasars flicker and measure their outflows with a precision that reveals the exact mechanisms that launch material at near light speed. We stand at the threshold of a new era of discovery, where the phantoms of the early universe may finally step into the light, ready to tell their long-held secrets. Could that brilliant, structured energy be a sign of intelligence? This is one of the most speculative and thrilling ideas ever proposed about quasars. What if we are not looking at natural cosmic engines, but at the ultimate feat of astroengineering, a project on a scale so vast it defies human imagination? The concept was first seriously explored by the Soviet astrophysicist Nikolai Kardashev, who envisioned civilizations so advanced their energy needs would be visible across interstellar space. A Type 2 civilization on his scale would harness the entire power output of its star, but a Type 3 civilization would command the energy of an entire galaxy. From our vantage point, what does a galaxy-spanning civilization look like? It might look exactly like a quasar, a single, impossibly bright point source radiating the power of 1 trillion suns. The structured jets, the precise flickering, the efficient conversion of matter to energy, all of it could, in theory, be the signature of a technology beyond our comprehension. Perhaps the accretion disk is not a natural whirlpool of gas, but a Dyson sphere of unimaginable complexity, a swarm of energy collecting structures built around the black hole to harness its gravitational power. The relativistic jets could be directed energy beams for propulsion, or even a form of interstellar communication, a cosmic lighthouse signaling across the void. This is not mainstream science, but it is a powerful exercise in questioning our assumptions. For decades, researchers in the search for extraterrestrial intelligence, or SETI, have occasionally turned their radio telescopes toward active galactic nuclei. They are not necessarily expecting to find a message, but they are checking for an anomaly, for a pattern in the noise that is too structured, too artificial, to be explained by known physics. They search for a signal buried within the quasar's broad emission spectrum that resembles a technological signature, perhaps a narrowband radio transmission superimposed on the natural roar. So far, every observation has confirmed the natural origin of these phenomena. The flickering is chaotic, the jet physics follows the laws of relativity, and the energy output, while staggering, is consistent with a gravitational engine. Yet the very act of looking forces us to confront the limits of our knowledge. If a civilization were truly 1,000,000 years ahead of us, its technology would be indistinguishable from the forces of nature. The greatest astroengineering project might not involve building small structures around stars, but taming the most violent objects in the universe, turning a destructive force into a sustainable power source for eons. The silence from these quasars is, for now, deafening, but it leaves us with a haunting question. As we map the cosmic web of dark matter and energy, are we charting the works of nature or the artifacts of gods? From the impossible brightness of a pinpoint outshining 1 trillion stars to the violent reality of stellar spaghettification, we have journeyed through 25 of the most bizarre phenomena surrounding quasars and active galactic nuclei. We have seen how their relativistic jets create illusions of faster-than-light motion, and how their flickering light acts as a cosmic clock, confirming the expansion of spacetime itself. We have explored the unified model, where a single type of engine appears as an entire zoo of objects based solely on our perspective, and we have located the universe's missing matter hiding in the shadows cast by their brilliant light. These monsters engage in cosmic feedback, capable of both birthing and quenching stars, while their binary dances foreshadow the most powerful gravitational wave events imaginable. They backlit the large-scale structure of the cosmos, helped re-ionize the universe, and their very existence in the infant cosmos presents the profound timing paradox of how they grew so large so fast. We have seen them as gravitational lenses mapping dark matter, as young radio sources still trapped in their own glow, and as residents of seemingly ordinary galaxies flaring to life during galactic collisions. Their properties follow a main sequence dictated by how voraciously they feed, and their legacy of heating the intergalactic medium has helped shape the universe's evolution toward a quieter future. From the phantom absorption forests in their light to the speculative, mind-bending possibility of astroengineering on a galactic scale, quasars consistently defy our intuition and stretch our understanding of physics. Each of these 25 points reveals a different facet of their profound enigma. So, after this journey to the heart of cosmic power, which of these bizarre quasar facts left you the most astonished? Was it the sheer efficiency of their accretion disks, the reality of ultra-fast outflows, or the cosmic mirage of superluminal motion? Share your most mind-bending moment in the comments below.